So good afternoon, everybody. There are not many of you here, but I wanted to make an announcement on behalf of the ASI. So the Astronomical Society of India, if you want to become a member and be a part of us, then there are membership forms which are available outside. It is a community and there are lots of announcements and so on and so forth. The reason I am also making this announcement is that if to become a life member, you need 2 publications. And you can also become a student member. You can check out the fees, membership fees. For the life members, it's only a one-time thing. For student member, it's for 5 years. And we are going to increase the fees from next month onwards. So if you are interested in becoming a member, you may please take the form. And you will find lots of life members here who will, support your recommendation. And you can immediately give it here today or tomorrow itself. And then we can process the application. So if you are interested, you may go ahead with that. So yeah.
Okay, so we have our first speaker, Mahavir. He will be talking about nature of galaxies, cosmic dawn to present. Yeah. Can use this one also.
So this will work, right?
This is both are fine.
Okay.
This is for
Hello everyone, am I audible? Right, so I'll be talking about galaxies and from cosmic dawn to the present. And the way I see the title now and the way I have arranged this talk, so actually it should be, from the present to the cosmic dawn. That's how the talk will evolve. So this is a kind of a diagram that I created. So basically, how does the nature of galaxies is important for the current status of observations in the field and the theories. So at low redshift, we usually measure the galactic main sequence of star formation, the stellar mass halo mass relation, the luminosity function of galaxies, and there have been a considerable amount of work that has been done both at theoretical side and as well as at the observational side, and surveys such as SDSS have been providing the information on galaxies and putting out these trends. Similarly, there is considerable work on the metallicity of the galaxies, and there are trends between the gas fraction, star formation rate, stellar mass and metallicity that are now well known, and theories have been constructed for those. However, at the high redshift, now the subject is kind of exploding, and so again I can categorize. So at high redshift, the nature of galaxies is important for the problem of reionization, because the first galaxies ionize the universe, and the effect of that and the progress of reionization is going to be measured by SKA, and there's a lot of information on the first galaxies that is coming up with the JWST now. There is another aspect that relates to the population of metal poor stars that we see in the Milky Way today. However, the behavior of star formation in the first galaxies that was detrimental to explain many of the peculiar abundance patterns, and Gaia is revealing all this information in its latest data releases. Okay, so before we go any further, so that you don't miss, so I will just give the answer or theme of this talk. So which is basically is a cartoon picture or a diagram that how do I view the evolution of galaxies. And so initially the galaxies are bursty, kind of a cranky, like starting an engine. So the star formation rate jumps up, comes down, and then slowly the properties of the galaxies, they settle, and it evolves towards a smooth behavior. So in time wise, the time for this initial bursty phase is very, very small, and most of the evolution is actually very smooth. So here I should add a point that even if I say that the evolution is very, very smooth, there do occur some exceptions, and you may find some really active starburst galaxy even in the present day universe. Okay. So, right. So how are the galaxies formed? So this is the current view of galaxy formation, where you see a forefront simulation of the cube of dark matter, and there are perturbations in that, evolving from very tiny values to the structures, nonlinear structures that emerge at smaller redshifts. So there are two key physical concepts, which is one is the self-gravity and the expansion of the universe. So growth of perturbations in an expanding universe. So I do a fair bit of teaching nowadays, and in the classroom the students might not be that well acquainted with the simulations. So here is a kind of a genes analysis or a Newtonian linear analysis in an expanding universe that gives quite a bit of answers about the galaxy formation, except in the nonlinear regime. And in fact, there is a very nice book if you want to do it purely analytically also. It's Cosmology by Weinberg that goes analytically to quite a far extent. Okay. So what do we, so but the forefront is basically the numerical simulations, and the structures form in the dark matter, and these dark matter structures, which are the nodes in these boxes. So inside that the baryonic matter settles in, and this is a simulation with both baryons and dark matter, which is the Eagle simulation. And then there you can see that in each filamentary node there at the cross junction, you have the galaxies emerging. Okay. So on the left on top is the number function of the dark matter halos that were formed, and there is a semi-analytic approach for that, the pressure sector or excursion set approach. With that actually explains the simulations quite well. So what is the another aspect? So taking from the halos, then we need to put the baryons in the halos and the stars form. So this is a stellar mass to halo mass relation that is obtained from Eagle simulation, and there is a lot of work being done to explain why the slopes are changing, but I'm not really concerned about that. To me, so if the higher is the halo mass, the stars are higher. So by that I mean the smooth trends. So the halo mass is evolving as the redshift decreases and the time increases. So is the number of stars and the star formation rate. Okay. So take it, whenever I say the word smooth, that's what I mean. So what is the consequence of these smooth evolutions? So one consequence is that you can do plots like this in the present day universe or at low redshifts. So this is for a change. So this is from the Illustris simulation. So here you see that there are these trends, I would say again the smooth trends, where the star formation rate would be higher if the stellar mass is higher, and the stellar mass is higher if the halo mass is higher. So I can predict that for which halo masses, what would be the stellar mass and what would be the star formation rate. So going on, if you want to do further for metals or chemical analysis, similar smooth trends can be derived. So here is a mass metallicity relation for Eagle simulations, and again with redshift at large enough time in the evolutionary history, we recover again the smooth trends. Okay. So I have said smooth quite a few times because I really want to emphasize that point. So there are a lot of models for galaxy formation. So I was trying to compile a list actually. So you can see there's Galacticus, Galax, Morgana, such as SAG, Santa Cruz, YSM, Galform, which is a popular one. So, and there are even bathtub model, and there is even a minimum bathtub model. So, and not to take away the rigor out of this, there is a lot of work that has gone in each of these models. So basically, so each of the models, basically you take a halo mass or a assembly of halos either from the simulation or from a semi-analytic approach, and then you populate them with the gas and then create some recipe for stars, and then you use some parameter to describe the feedback, and then try to predict the behavior that I showed you earlier. Right. So we thought that okay, to explain the same smooth evolutionary trends, can we build a model which is not with these traditional coupled equations of mass balance, but rather with energy balance? So what we were looking at in Eagle simulation was the energy or the total energy of the halo, and notice a minus sign is there. So when the curve increases, the actually is actually decreasing energy. So with time, what happens that the halo is accreting the gas, and that's why the energy is decreasing for the dark matter halo. But the blue curve shows you the same for galaxy, the baryonic stuff, and for that, it more or less stays constant after the initial phase. So that tells you that somehow the negative energy that has been created due to accretion is somehow balanced by something. So can we use this energy balance argument and build an analogy with something similar happens in case of stars? So for example, the main sequence stars. So when there are radiative losses, the energy goes down. However, that is compensated by the nuclear energy generation at the center of the star. So that balance is somehow maintained here as well. In galaxies, we can see that the balance is there. And in fact, it is created by the formation of stars in the galaxy. So because of accretion, the total energy goes down, say for a small instance of time, but it is balanced by the star formation in the galaxy. So because this is an energy argument, so and it's minimal assumptions we use, so we could come up with an equation that is as simple as this one, and we didn't want to really complicate it and try to get as far as possible with this equation. So right after this equation, where we put in the star formation rate with some sort of supernovae parameter velocity, so this energy is provided by the energy that the decrease of energy due to the accretion. So this allowed us to calculate the star formation rate of the galaxy, and that is shown here. So we were able to recover the main sequence, and we compared it with Eagle simulation, and Eagle simulation is a fairly good description of the actually observed galaxies in the universe. So that we were able to explain the main sequence of galaxy quite well. And the main point here, why you have a higher halo mass and then stellar mass and SFR, the smooth trends, because these quantities evolve smoothly over the entire regime of low redshifts. Okay, and then we can build on, basically we took that same thing and put it into a chemical analysis model, and there again we find similar smooth trends easily recovered, like the mass metallicity relation. So the whole point to make is that, okay, so we used the energy argument, and we were able to explain the smooth evolutionary history of the universe. And the main point, that indeed the evolution of the galaxies is quite smooth, that gives us the trends between the MH, stellar mass, and SFR. Okay, so we can explain the evolution of galaxies and reproduce the observed trends well. So can we extrapolate the same thing now, if we do have a behavior of star formation, let's say, and then go to the higher redshift and explain the reionization. In fact, that's precisely being done in the community. So this is a popular model 21 cm fast for reionization, whereas you can see that basically what you get from cosmological simulations of dark matter is the number of halos. And in each halo, then you use a parameter to put some gas in it, and then some parameter for an efficiency of star formation, and then for some parameter that how many photons that are produced by stars will escape the galaxy. Right. So in fact, from these works, so the conclusion that you will reach, because there are far too many low mass halos compared to high mass halos, so you'll obviously conclude that the universe was reionized by the faintest of the galaxies. So that's not a difficult conclusion to reach. You can already see it, because you are doing it through these parameters, which are more or less constant parameters, and basically directly from halo mass with these parameters you arrive at the photons. So that was the say the traditional viewpoint that always was held along, that the universe was ionized by faintest of galaxies. Right, and in fact, one of the major drivers for JWST was that HST is not able to detect, but the JWST will detect those faintest sources. But the question is it correct to extrapolate the smooth trends that we see, for which we ourselves build the model, and even extrapolate them to higher redshifts? That's the question. So the answer that you will see So there is a hint that we have in the scatter plot, for example. It's roughly the same plot. X-axis is the halo mass, y-axis is the star formation rate. But as moving from redshift 2, which is fairly low, to 6, very high redshift, we find that towards the lower stellar mass, the trend is not really smooth. So the color shows you where most of the points are located. In fact, the galaxies are kind of bunching in this sort of bimodal behavior, where they either have a very high star formation rate or they don't have any star formation at all. So by that you see that these galaxies, if they have that much star formation rate in that halo, and the luminosity is a direct function of star formation rate, so they can't be faint. So they got to be brighter. I mean, not as bright as in the current universe, but brighter than the faintest for sure. So it's because this is the real plot now. Initially I showed you a cartoon, and you believe me on this one. So this I plotted for one galaxy in Eagle simulation, and the same plot will be recovered for almost all the galaxies in Eagle or Illustrious or any other fire or gasoline or any other simulation you see. Initially when the galaxy forms, it has this cranky behavior that it forms abruptly the stars, and then all of a sudden star formation rate goes to 0, and then literally behaves towards or moves towards the smooth behavior. Okay, so and because of that up and down, you have this lot of scatter towards the low mass end at high redshift. And the reionization is not a consequence of the halo mass. Reionization is a consequence of the stars. So why to just deploy a constant parameter with halo mass and do it? Why can't we just do it with straight from these galaxies from Eagle with the star formation rate? So that's exactly, there is even more an appropriate parameter, because the galaxies at high redshift are compact. So appropriate quantity would be divide the star formation rate by area, which is the surface density of star formation. There the same effect is even more amplified. The high redshift galaxies are brighter and very high value of sigma SFR. So this is the same plot done in this. So imagine that these galaxies, very high surface density of star formation, they would have a porous ISM, and if I associate that only these galaxies are allowed to reionize, then this is the reionization history that you would recover. So we find that in fact the universe was reionized by galaxies that are within the current detection limit of the Hubble, and we wrote the title of the paper, The Brighter Galaxy Reionized the Universe, which is, we ourselves thought was very provoking in a way. But then we thought, what about the JWST? What will JWST going to detect then? Because the main target was the faintest galaxies. So then we added a line which was JWST will study them in great detail, the galaxies that reionized the data. But probably should have done more. But anyway, so then comes to the December 2022 and the JWST revolution. So JWST started detecting the galaxies at high redshift. So these are galaxies, for example, now redshift 10 becomes a commonplace. So at 10 and 12. So not only that, so 4 galaxies here detected at 10, 12, 11 and 13, okay? Right, so this is something, so the redshift can be determined both ways. So you can do photometry and detect it, or you can do spectroscopy. So it has both the instruments, an IR chem and an IR spec. So how do I, so whatever knowledge of observation so it's like if I am looking at the faces in the crowd, and if I say some gray hair or white hair, then I may conclude that the person is old. But when I look closely, or maybe do a spectroscopy, or maybe a DNA test, then I would find that maybe it's a blonde person from Western countries. So something like that. So the spectroscopy reveals or confirms the redshift of the galaxies. So it's the spectroscopic confirmation of those same 4 galaxies in photometry that was published recently, and they confirmed that the redshift of these galaxies is 10 to 13. Now I was hoping when I started reading this paper, it appeared in December, that they would be giving me star formation rate, and more than so they would be giving me the surface density of star formation. And they gave me the star formation rate and the UV magnitudes, which are not very low. So these are the brighter galaxies that we were calling in our own paper. And in fact, there was a paragraph that we found where they said exactly the same thing to the galaxies with very high value of sigma SFR, which is 15 to 180 for these galaxies, that reionized the universe. And they cited our paper there. So so looking at these values of sigma SFR, now for myself I could straight away do was to put those galaxies on this plot. So that's the regime they will occupy on top. So faintest, which earlier you would claim, if you just map the halo masses to the stellar masses and star formation rate, then the left side of this plot will be the one that reigns the universe. But JWST is finding them there. And in fact, this box is increasing towards the right side. So that I found another paper here in which all these galaxies were now, almost 13 of them are compiled, and I am hunting for the sizes of these galaxies. Okay, so I am towards the end of my talk now, and I will leave you with conclusion. And I was thinking, what is the best conclusion? So, to all the young people out there, actually not young people, sorry, so I should be maybe adventurous and young minds out there, this is the best time to work on this, because the JWST is coming up almost weekly or daily new observations. So that is all from me. Thank you.
Thanks, Mahavir. Questions? Jasjit?
Nice talk, Mahavir. Now, in the modeling which you are talking about, there are several models which also talk about coevolution of AGNs and galaxies, black holes and galaxies. More and more observations are suggesting that there were large disks and quenched galaxies or quiescent galaxies already in place at reasonably high redshift, like 6 to 7. So, what do the models have to say about that scenario? Because I have seen several simplified analysis which say that that is simply not possible in LCD. But I have not seen any statement from people who work on SAM. So I would be curious to know what you think of this.
Yeah, so there are two ways. One is change the IMF, but the other one, which have been some of the papers that I was looking at, is through the cooling is more efficient, and somehow you pass through the entire evolutionary history by running out of the gas reservoir. But it's a very unsettled problem. I agree with you there, and even I'm thinking about it and looking for more. But that you are specifically talking about redshift 6, right? 6. Okay, yeah. Sure.
Any other question? Nadine?
Yeah, just a comment. I mean, so when we have seen that the bimodality in the star formation rate, which is actually pretty common in local dwarf galaxies with low metallicity.
So that are exceptions at low redshift statistically.
Right, right.
So this plot, for example, here, so the blue is all the SDSS galaxies at low redshift.
Right.
And see, two exceptional galaxies plus and cross that is shown is actually blue at low redshift.
Right.
But most of the galaxies, as the histogram shows, are following the trend that's there. So I would say it's less than 1% those which you are talking about.
Yeah, I mean, I agree with you. I mean, but at high redshift, things might be different.
At high redshift, it's more common. There's the same histogram there. Mostly all the galaxies have that abrupt behavior of star formation. So you can't have just one-to-one mapping between the halo mass, the stellar mass, and the star formation.
Exactly.
Yeah.
Any further questions? If not, let's thank Mahavir once again. The next talk is by Ishwaraya Chakali on multi-wavelength dust polarimetry and the role of the magnetic fields. Ishwar.
Yeah, good afternoon, everyone. Myself, Chakli Israya from ISAT Tirupati. I'm a Ramanujan fellow there. I thank Scientific Organizing Committee for giving this opportunity to present my work on multivalence polarimetry and role of magnetic fields. So since I'm mentioning the magnetic field lines, it doesn't mean that I'm talking about only magnetic field lines, but it involves the interplay between magnetic fields, gravity, and turbulence. So this work essentially has been done in a large collaboration and also with a small group at ISR Tirupati. These are my students. So this is the overview outline of my talk. So half of my talk may be dedicated to the brief review on the magnetic field lines. How do we measure them, and what is the relative importance of magnetic field lines in comparison to other parameters such as turbulence and gravity. And I'll take one case study and present the results based on the magnetic field lines. So these B field lines we traced based on the multivalent polarimetry. And so this is the case for only the region which is entirely free from stellar feedback and other complications, turbulence and etc. And end my talk with summary. So main motivation behind my work lies in this slide. These are the two main questions I just would like to put in front of you. That how the cloud accumulation process actually takes place in the interstellar medium. Because if you see at the diffused interstellar medium, the density is very low, 1 particle per centimeter cube. And if you see at the molecular clouds and their corresponding fragments such as clumps, cores, the density is typically higher than 1000 to 10 to the power 4 per centimeter cube. And so these clouds mostly found in a kind of filamentary morphologies. If you see, this is a typical molecular cloud of Taurus region. And you can see that dense elongated filamentary-like structures. And there are also low density regions called striations, which are maybe supplying the material from low density to onto the high density portions. And if you see the distribution of dense cores and protostars, they exhibit very nice configurations such as a chain of cores or chain of protostars, as shown in this figure. Okay, the background image is the column density map, and this various symbols are corresponding to the distribution of dense cores and protostars. You can see how well aligned these filamentary structures and cores and protostars along these dense ridges. So there is a well connection between the large scale molecular clouds to small scale clumps, cores, and protostars. And high resolution ALMA also revealed that these protostellar disks, and these are the progenitors to form the planets like our own. And the question is that what are the ingredients that are involving in this process? Formation of clouds to and then collapsing in the substructures to form the stars. What observations reveal is that indeed magnetic fields an important role. They play an important role. If you look at the structure of the filamentary-like structures, as shown in this diagram, the background is the column density map, and these vectors are actually correspond to the B field orientation. So the red are actually traced by optical polarimetry, and then cyan are corresponding to the B field orientation revealed by the NIR polarimetry. You can see that there is a preferential orientation between the filamentary-like structure and the B field lines. So there is a perpendicular orientation between the filament and the B field lines. So they indicate that B fields are indeed play an important role. When we look at the gas kinematics, so this is one of the important results from this work. So they reveal that indeed these filamentary-like structures can form because of the converging flows, large-scale converging flows. And in this process, B fields can channelize these flows to form the elongated filamentary-like structures. So in a way, the star formation is a two-step process. At first hand, turbulence and magnetic field lines actually collaborate with each other, and then they form an intricate network of filamentary-like structures. So turbulence in the large scales actually can sweep up the interstellar medium, can help in the accumulation of the material, but magnetic fields can try to help these flows. And then once you form the filamentary-like structures, gravity can take over. It can govern the further fragmentation and collapse of these cores. But as I mentioned, there is a collaboration. Okay, they actually interact with each other and they govern the cloud formation. So when we just have only gravity, as shown in this red curve, so the star formation could be very, very high. Like all the stars should be forming very, very efficiently, something like hundreds to thousands of stars per year, and then the cloud lifetime should be only 1 million a year. But actual observations indicate that the molecular clouds can live up to 10 million a year. So what are the ingredients that can stabilize the clouds against gravitational collapse? So when we introduce the turbulence and magnetic field lines, etc., so these two factors can counteract the gravity, then they can prolong the cloud collapse, and then so through this clouds, the molecular clouds can live up to 3.5 million a year. But what about the other factors such as jets and protostellar outflows? So since the turbulence is the intermittent phenomena, this turbulence can decay very easily. So turbulence can decay within 1 billion year or so. In order to replenish the turbulence, we should have the protostellar jets and outflows. So if you have all these factors, then the star formation rate, we can able to produce the observations. So the shaded areas correspond to the observations, and these are the simulated results. So indeed, what I want to say is that in addition to gravity, we should have the turbulence and magnetic fields contribution. And as I mentioned, so each factor cannot participate solely. They can influence, they can interact with the other factors. As shown in this Venn diagram, magnetic fields can interact with turbulence. If the magnetic fields are stronger, the magnetic fields can channelize the subalphonic turbulence. If turbulence is stronger, so supersonic turbulence flows can compress the magnetic field lines. And in the second hand, if you take the interaction between the interaction between gravity and magnetic field lines, if the gravity is stronger, and gravity can drag the magnetic field lines towards the core. If the magnetic fields are stronger, so these B field lines can channelize the gravitational collapse and so on. So what we really want to study is the relative importance of magnetic field lines in comparison to gravity turbulence, which is poorly understood because we do not know how they interact with each other across the scales. So for instance, if you look at the diffuse interstellar medium, so major contribution actually comes from the turbulence and then magnetic field pressure. These numbers correspond to the pressure values. And if you look at the thermal pressure value is very, very small and negligible. So this is the case in the general diffuse interstellar medium. And the fourth one is correspond to the gravity. Okay, so this is the case in the diffuse interstellar medium, but we do not know what is the case if we go towards the higher and higher densities. And so this B field configuration or the strength won't remain constant across the scales, but they actually tend to change. So these observations came from the Zeeman measurements. This work revealed that up to certain density or column density or number density, the B field strength is remain constant up to something like 6 to 10 microgauss. But after some threshold density, the B fields can scale with density by 2/3 power law. So actually, B field lines can actually act like a switch. Up to this critical density, magnetic field lines can help in the channelizing the material flows. But after critical density, they can counteract with the gravity and stabilize the clouds from gravitational collapse. So if you see the measurements, there is a gap, various gaps you can see. These are actually resulted from H1 observations. These are from OH, and then these are from CN. And this is where we really don't know exactly the switch is happening here or somewhere is shifting towards either end of the gravity. And the same inference can be made based on the dust polarimetric observations. And what about the turbulence? So this is one of the best depiction of turbulence in the early days by Leonardo da Vinci. As shown in this diagram, turbulent flows can actually counteract with the gravity, and then it can stop the cloud accumulation. And the turbulence is also can be quantified using the non-thermal velocity dispersion, which is also not constant across the scales. As shown in this diagram, at the smaller scales, the turbulence can be subsonic, and at the higher scales, it can be supersonic. And there is a well-established, power law relation between the turbulence and spatial scales. So it is what we infer until now is that it is always easy to measure gravity and turbulence, but it's very hard to quantify or measure the magnetic field lines, because the intrinsic constraint is that in case of intensity, we can take snapshot and then measure the intensity. But if you want to measure the magnetic field lines using dust polarimetry, for example, we need to have 4 times of that observing time. And also, until now, the observations exist in a kind of patchy-like structure. We want to have the observations from large scale to small scales in a coherent picture. As shown in this diagram, this is the just kind of for school kids I have prepared. And if you have a bar magnetic and then spill the iron filings, we generally can see the B field orientation with the closed loops and open loops. But if you just look at the one piece of iron filing, it can give the direction. But in case of interstellar medium, how can we measure the magnetic field lines? So this actually result from the stellar polarimetry, which revealed that in the galactic plane, B fields are mostly in parallel to the galactic plane, but some places there are actually accelerating a loop. So we use dust polarimetry to measure the B field orientation. The major constraint from the dust polarimetry is that we cannot infer the direction, but we can only infer the orientation. So according to the dust polarization mechanism, if you have a unpolarized light which is coming from the distant astronomical sources, for instance, if you take 2 components, red and blue, red component can encounter maximum extinction cross section, which is caused by the aligned dust grains which are non-spherical and spinning with respect to the magnetic field lines. And whereas the another component, blue, can easily pass through because it encounters minimum extinction cross section. Because of this differential extinction process, the outcoming light will be linearly polarized light. If we know the direction of this electric vector, we can trace the magnetic field orientation, but not the direction. So the detailed process involved in the dust grain alignment will be discussed by my colleague Archana So in the next talk. And again, I am going back to the observations. Thanks to the Planck observations at sub-millimeter wavelengths, even though it was actually a very low resolution of 5 arc-minute, so the Planck actually mapped the magnetic fields in the entire galaxy. So these are the results from Planck polarimetry. The problem with the Planck is that we cannot trace the magnetic fields in the dense structures. So it can confine to the like maybe greater than 0.5 parsec for the nearby star-forming regions. So one of the main important result which actually came from Planck is that in most of the molecular clouds, you can see a perpendicular configuration between the dense filaments and the magnetic field orientation. So it indicates that B fields indeed play an important role in the low density regions. What about the role of magnetic fields in the dense structures? And before going to the further talk, so this result we can also understand in terms of the B field orientation versus the cloud configuration. So there is a kind of bimodal distribution is actually prominent, is clear. If you see towards the central portion of our galaxy, even though these clouds are separated by a few tens of parsec, in one cloud the B fields are perpendicular to the cloud, in the another cloud they are parallel to the clouds. Okay, this is because of the interplay between the gravity and turbulence. And so it's the same kind of result can be inferred by the shape parameter. So this positive values actually infers that the cloud structures are preferentially parallel to the B field lines, and then in this portion, these are actually in the low density. So if you look at the same result in the high density regions, there is a perpendicular configuration is prominent. So so these are kind of different kind of results resulted from different people, but they all infer the same result. So in the low density regions, B fields are tend to parallel to the structures, but in the high density regions, they are preferentially in the perpendicular direction. So this is what we want to know. But the problem with the Planck and then optical near air polarimetry is that we cannot trace the magnetic fields in these smaller scales, of 0.2 parsec at 150 parsec distance, because optical and NIR polarimetry can only trace the magnetic fields in the low density regions, and the Planck has its intrinsic problem with the low resolution. And then if you look at the simulations, for example, if you have simulations with strong magnetic field lines of the order of 120 microgauss, and they play an important from larger scale to smaller scales. So the orientation won't change if you look at the across the scales. But if you look at the protostellar scales up maybe the 3000 AU, because of the ambipolar diffusion, the B fields can exhibit hourglass shape like structure. Indeed, this has been observed. So if B fields are stronger, they are supposed to play an important role from larger scale to small scales. But observations actually give the surprise. For example, if you have even just look at the more denser regions as shown in this diagram, even though there is a preferential perpendicular configuration between the filament orientation and the B field orientation, but because of the gravity flows which are causing along the filament, so there is a departure from the perpendicular configuration. And if we have a H2 regions, for example, expanding ionizing fronts can distort the mantle field lines into bow-like structures. And if we look at the very, very small scales using ALMA, if we have dominant outflows, they can also distort the mantle field lines. And we cannot really study their importance. And if you look at some of the reasons with the dominance of turbulence or weak B field lines, so the B field lines clearly distorted from the coherent configuration. So in order to study the real or the intrinsic role of magnetic field lines, we should try to select a region which should be free from quiescent, and it should be hosting the pristine conditions. One such example would be torus B213 region. And here every vector actually corresponding to the B field orientation resulted from multivalent polarimetry. You can see that there is a preferential orientation, a kind of perpendicular configuration towards this torus B213 region. But the problem with this this region is that these are nearby and very faint, and there exist no submillimeter polarization observations towards this such kind of regions. And this is one of the best example for the cloud which is forming the low mass stars like our sun. And so we have conducted very sensitive dust polarization observations using JCMT Scuba 2.2, which is a very sensitive polarimeter. Installed on 15 meter JCMT telescope. Please remember that there is a ordered B fields in the larger scales. So this is very surprising to see the kind of B field orientation and in the smaller scales. So these are the result. So you can see that I showed in the previous diagram is that there is a kind of elongated filamentary-like structure, and it actually have some kink-like orientation, and it is pretty straight filament, but with some kind of kink-like structure. But if you look at the B fields at the smaller scales, the yellow vectors are yellow segments are correspond to the large scale magnetic field lines, and this red are correspond to the mean B field orientation in these dense cores. Only one core B field is actually matching with the large scale B field, but not the other cores. And you can see the direction of outflow is also well matching with the core scale B field and also large scale magnetic field lines. In rest of the cores, they are not. They are clearly deviated from the large scale uniform magnetic field orientation. What I would like to highlight is that these two cores are actually hosting the protostars, and their mass and their entire age, etc., everything is similar. So we generally say that these two cores actually are twin cores, but their magnetic field configuration is entirely different. This is just these are all about the relative orientation between the large scale magnetic field versus small scale magnetic field. I'm just talking about the orientation of the B fields. But what about the energetics? So B field strength can be estimated indirectly if we know the density and then non-thermal velocity dispersion and then dispersion in the magnetic field lines. We can estimate the magnetic field strength using this famous DCF relation. And it involves some basic assumptions that turbulence is isotropic and incompressible, and then fluctuating magnetic energy is actually corresponding to the non-thermal velocity dispersion. If we take the ratio between this turbulent component and then ordered B field strength component, so these are proportional to the non-thermal velocity dispersion to the alphonic velocity. And then whatever the change happens in this ratio, turbulent B field strength to ordered B field strength, that would directly reflect on the dispersion in the magnetic field lines. If we have more turbulence, the B fields can actually can exhibit more distortion. And if you have less turbulence, this sigma theta, or the dispersion in the B field can be smaller. And then there are new developments in this DCF relation. There is a new result by Scully synthesis in 2021. They have, they try to modify the DCF relation by treating the turbulence in a different way. They consider that turbulence is non-isotropic and compressible. So if you do that, I think this is the relation they have come up with. And so if we use this relation, our B field strength will systematically go down by 1.5 to 2 times. And so there are multiple kind of methods called DCF modified methods. For example, Hildebrand et al. 2009 and Howdy et al. 2009. They have actually proposed the structure function analysis to directly estimate the the ratio of the turbulent to ordered B field ratio. And so if we want to create a large scale magnetic field strength map, we can use there are different techniques have been adopted. So by following these methods, we can also construct the magnetic field strength map. So earlier days, actually people used to just come up with the single value on magnetic field lines, but these days it is possible to come up with the magnetic field strength map. So this is possible because of the high sensitive polarimeters as well as wideband polarimeters. And then there are two important metrics. If we want to understand the relative importance between the magnetic fields and turbulence, we can actually estimate the alphonic Mach number. And then to understand the relative importance between magnetic fields and gravity, we can use this mass to flux ratio criticality. So by knowing this parameter, column density and magnetic field strength, and also this non-thermal velocity dispersion, we can actually comment whether the B fields are stronger or weaker in comparison to the turbulence and gravity. And then coming back to the course that I have been talking about, two protostellar cores. So these are twin cores. They have exactly same properties, but if you look at the magnetic field strength and the mass to flux ratio and the alphonic Mach number, they're same for both the cores. So all the energies are in equipartition. So even though this protostar at the same evolutionary stage, and all the energies are same, but their magnetic field morphology or magnetic field properties are different. Their orientation especially is different. So we go on and try to come up with the velocity gradient map by taking the N2H plus data from IRM telescope. So these black vectors are actually infers the gas motion, which is actually inferred from the velocity gradients. And then this red vectors are correspond to the B field orientation. So in one core, you can see that this gas motion and then B fields are perpendicular to each other. This could be due to the rotation of the core. But in the other case, the velocity is very complex. There seems to be two converging flows are coming and then they are merging at the location of the core. So in a way that even though the cores are lying at the same evolutionary stage, the gas kinematics can change the B field orientation and that corresponding role. So this work is actually been published in Epicenters. So as I mentioned, these gas flows are not only complex in the small scales, but yeah. So this complex B fields could have been caused by the large scale converging flows I showed in the first portion of the presentation. So these large scale flows could be colliding at this location, and then they're actually inferring, they're actually twisting all the kind of B fields at the smaller scales. So and if you have these colliding flows at the location of filaments, and there could be a fiber-like structures can form, and then this kind of process can also change the B field orientation at the smaller scales. And indeed, this is the portion. This portion you can see that the B fields are quite ordered in the larger scales, and at the smaller scales, as I showed from the JCMT, the B fields are quite complex. And so some portions very close to B213 have also been observed by SOFIA. So this portion is called B211. So this was observed by SOFIA. And indeed, if you look at the B fields in some of the portions, B fields, they are actually complex. And the same thing had actually been observed by recent, JCMT Pole 2 observations towards this B10 cloud also. And then we actually continued our, efforts. So previously we had limited vectors in this region, We have done extensive polarization observations, and you can see the density of the vectors are large now. We mainly perform the optical and NIR polarimetry. So here the red vectors are actually come from optical wavelength, and cyan are from NIR polarimetry. And so this, we know the B field structure at the small scales. So by combining the large scale information and the small scale information, we try to come up with this kind of interesting relation between the column density and the B field orientation. You can just see that the B field orientation is almost constant in the low density regions, up to 6 magnitude, and there is a data from JCMT. You can see that the B fields, B field is quite complex, but there is a gap between 6 magnitude to 10 magnitude, and so this gap actually being filled by SOFIA. SOFIA can fill this gap, and so by having the multivalent polarization observations, we can actually come up with a coherent picture into the relation between column density and the B field orientation. And also, if we know the B field dispersion and other information on gas velocities and all, we can actually construct a relation between column density and the B field strength, and alphonic Mach number, and also mass to flux ratio. Thanks to my students, we have come up with beautiful posters. One of my students is working on the role of Mantle fields in the massive star formation. So you can visit and then give some comments. And another student is working on the G1 project based on the fast telescope observations towards Planck galactic cold clumps. And one Vijay is working on the dust polarization properties in the interstellar medium as well as the intracluster medium, and try to understand the impact of stellar radiation on the dust grain alignment efficiency. Yeah, I stop it here, and thank you.
Thanks, Ishwar. Questions? Jasjit?
Yeah, you mentioned that magnetic fields have the ability to slow down collapse and star formation, so they can in some sense modulate star formation rate in a molecular cloud. Now, would this also apply to population 3, where magnetic fields may not be there or may be weaker? And do you think this could contribute to a qualitative difference between the earliest star formation and what we have now?
Yeah, that's indeed a very good question and tough question to answer. So nobody knows, about the magnetic fields in the early universe. So, yeah, since the metals could have been very weak, B fields could be maybe weaker also. So they may not be that much efficient to govern the entire star formation. Yeah, that's what I believe. Mm-hmm. Yeah.
Or battery to build the strengths up when the first star formation happens. So the strengths are likely to be much weaker.
Yes, that's right. Yeah. So if you don't have counteracting forces, I think for gravity can take over much easily. Yeah.
Any further questions? Yeah, there. Yes.
I have a question regarding the estimation of magnetic field using DFC method. So in the new method, can you comment on what are the new changes? Like, I can see they have included the non-thermal velocity dispersion in the new method.
Yes, I'll go quickly. Yes. So the previous relation consisting of square root of 4 pi rho, and there is no square root. So, and this method can systematically underestimate the B field strength. So generally, if you see the one general observation from our kind of close, let me go to the this one. Yeah. So if you see the G1 measurements versus dust polarimetric observations, most of the B field strength are systematically larger than the G1 measurements. So even though this is line of sight component and this is a plane of the sky component, there is a huge difference. But the ST method, I think is encouraging that it can estimate systematically lower B field strength. Yeah.
Okay, thank you.
Thanks, Ishwar. Now let's move on to the next talk of the session by Archana Swan. She'll be talking about magnetic fields and dust grain alignment in different environments of galactic star formation. Archana.
Hi, good afternoon. I think I'm audible. Thank you, organizers, for giving me this opportunity to show my work here. And thanks, Ishwar, for decorating the stage already for me on magnetic fields. In my talk, I'm going to show my results and say a little bit about, I think this is good enough. The green one was a little intense. So magnetic fields and the dust grain alignment in different environments of star forming regions. I will be mostly talking about the galactic star forming regions, and that too with the regions making low mass stars. Most of this work is done in close collaboration with many people actually, thanks to them. And along with that, okay, let's move. So we talk about magnetic fields, role of magnetic fields in various processes. But dust grain alignment is the most integral part of understanding magnetic fields in the galactic star forming regions, if I talk about that only. So I have shown this slide here where I'm showing an overview of like all sky magnetic fields produced by Planck, and I'm also showing a dust grain picture here, and these two things, these two understandings are interrelated and they are very important. If you want to understand magnetic fields, you have to understand dust grain alignment if you are just doing dust polarimetry. So my talk, I am dividing it into two portions. One is about magnetic fields in the ISM, where I am going to tell you a little bit about their importance in the star formation. Second, on how they behave at different scales and also in different environments. The second part of my talk is about the dust grain alignment in the interstellar medium. And I'll give a little introduction on the dust grain alignment, different theories. What are the broad questions about dust grain alignment? And what are the observational tests and evidences available till date? And an overview. So the problem starts with star formation. And Ishwar already told about that how magnetic fields are important in the star formation. Locations of star formation are molecular clouds, which are the sites of rich gas and dust with densities of more than 1,000 particle per cubic centimeter. So molecular clouds are the sites of star formation. Let's proceed. So locations of star formation are mainly found in the filamentary clouds. And in these filamentary clouds, we actually have the protostellar cores embedded in here. So when you see these regions in different wavelengths, you see the elongated structures, for example, in Planck continuum maps and also in the Herschel continuum maps. But if you go to the high resolution observations, for example, from ALMA and IRAM, you can see the continuum embedded cores in these filaments where the real star formation is going on. Now, I'm still talking about star formation. Now, why we need magnetic fields? At the time of World War, when many Europeans were coming to US, there was a problem in the migration, and only some of them could make it to the US. So similarly, we have a lot of material in our galaxy. We have lots of gas, lots of dust. Then why our star formation rate is just 1 solar star per year? Culprits are here. So these are the components which are responsible for regulating this rate of star formation in our galaxy. And magnetic field is one of them. So gravity, to make stars, it has to compete with various forces. And magnetic force is one of those forces. So that's where we start investigating magnetic fields in different star forming regions. Now, we're talking about magnetic fields. So there are techniques now we know these days that can be used for finding magnetic fields. For example, Faraday rotation, synchrotron emission, polarized dust emission, starlight polarization. In this slide, you can see that the information is coming in bits and pieces. So you have to specify your problem on magnetic fields when you talk about understanding magnetic field in different regions. In my most of the research I'm doing and I've done, I'm just considering polarization due to thermal distribution and also the starlight polarization for interpreting magnetic fields. Let's start with the bigger picture. Actually, I was told to give an overview of the subject, so I'm just starting with the bigger picture here. The bigger picture is given by thanks to Planck on this the all sky magnetic field map. But when you see the roles of magnetic fields at different scales, for example, in the in other galaxies also, they are helpful in regulating the mass and the energy flows along the outflow orientations. If you go to the central part of the galaxy, you see that the stars are found connected with the magnetic fields around the black hole. And the big triumph came in 2021 when we were able to find magnetic fields in the black hole. But most of my research focuses around the nearby galactic star forming regions. So that's why I'm just highlighting these star forming regions where I do dust polarimetry and the starlight polarization for getting magnetic fields. Problem with Planck, especially for me, was that the resolution was not enough. Planck is giving overall structure of the magnetic fields in the extended structures in the galaxy. But we wanted to see what is happening to the magnetic fields at very small scales and how the energies are doing at the smaller scales, not on very large scales. So we had to move to different facilities for observations in different wavelengths. For example, near infrared we did from SERPOL at IRSF, JCMT for submillimeter, ALMA for submillimeter, and optical. The journey started with Sampunavan telescope at ARES, optical polarimetry, and far infrared polarization from SOFIA, which is unfortunately now decommissioned. So using all these observations over a course of last 7 to 8 years, we produced samples of magnetic fields, information of magnetic field in different regions, and the regions which are embedded in different environments, depending on whether they are in harsh environment with the high energy radiation or whether they are just isolated quiet cores. So magnetic fields found in filament, for example, this work was published in 2019 in G34 filament, where we see that magnetic fields are mostly perpendicular to the higher elongated higher density region, as Ishwar also showed some of the results, but it is changing at different regions. And in the cores where exactly the star is forming, the outflow is shown with this black double headed arrow. We have found many such regions and found magnetic field properties in these regions. Similarly, we moved to the different type of regions where they are exposed by high energy radiation from O and B type stars. And we collected a lot of sample in those regions and investigated the properties of magnetic fields in those regions. So these are 3 different categories which were published as 3 different problems on magnetic field properties. Are scales important? Yes, scales are important. We have found magnetic fields changing from larger scale to smaller scales. Like Ishwar also showed some of the results. So if you see G34 filament itself, I'm just showing one example here. In the Planck, most of the magnetic fields are northeast to southwest. But when you probe magnetic field in the same region using longer wavelength, submillimeter, you do see a change in the magnetic field at different locations. But if you go further deeper, using different more sensitive observations, then you do see that yes, magnetic field lines are changing at much smaller scale where exactly the stars are forming. So yes, scales are important because magnetic field energy is changing over the scales. There is a poster by my student Siddharth on how magnetic fields behave in different environments. I'm not going through this slide, I'm just highlighting it here. So I'm not showing many results on magnetic fields because this was already shown. So I'm just giving an overview of roles of magnetic field. They regulate star formation by giving an ordered shove to the accreting gas and competing with different energies, for example, kinetic and gravitational energy. They modify their geometry when you go from larger scale to smaller scales, from lower densities to higher densities. And their surroundings play an important role because if you put a region in a harsh environment, for example, environment full of high energy radiation, the magnetic field properties and also their geometry changes. This was just overview on the magnetic field. Coming to the second portion of my talk, for understanding magnetic fields, we must understand the techniques which were used for interpreting magnetic fields. So ISM dust grain alignment, you remember he showed one image where most of the elongated grains were aligned with the magnetic field lines. So magnetic fields are interpreted, because I showed that I am just going to the dust polarimetry and starlight polarimetry, dust grain alignment. It was not easy. It was not easy to find the techniques which could help us in interpreting and finding the magnetic field geometries. So it was a huge effort from many people over last many decades who established the theories of grain alignment in the interstellar medium. It started with some people like Edwin Purcell, and Bruce Rayne is still working on it, and Leverett Davies and Greenstein. So many of them. Actually, they worked on understanding the grain alignment in different environments and different type of dust compositions. So a very nice compilation of all these grain alignment theories which were put forth in last 20 decades were compiled by P.G. Anderson in his review in 2015. This table here itself summarizes all the theories which were put forth for understanding grain alignment. For example, it started from Davis-Greenstein, then it went to super paramagnetic, then suprathermal, mechanical, and lastly, RAT, which is radiative torque alignment. I'll come to that. But when you put some theories, you have a bombardment of many tests and questions. So it should be helping you also, it should be tested observationally. So there are many tests which should be done on these theories. So there are many tests which are put here in the various columns. I am not reading them out. But the colors here, green color here shows that the theory which is showing green plus is directly observationally tested, and observations support that. The red one shows that direct observational tests are there, but there are some contradictions also. So you can see some red minuses there. The gray ones were nowhere, like there were no predictions and there were some ambiguous results. So at the end of the day, we were left with RAT, which is radiative torque alignment. Let's see what it is. So when the ISM is filled with anisotropic radiation, we all know that. So when a condition is fulfilled where anisotropic radiation of wavelength less than the diameter of the grain hits the grain, the asymmetric grains. So this is the condition you should put in mind, that these are asymmetric paramagnetic grains which were assumed in the theories. When the anisotropic dust grain radiation hits the dust grains, the grain starts spinning. And in the lowest energy state, the situation is that the shorter axis of the dust grain is parallel to the magnetic fields. Or I can say that the dust grains are aligned by the interstellar magnetic fields in such a way that their minor axes are parallel to the interstellar magnetic field. So from where the initial push comes from, that comes from the interstellar radiation field, anisotropic interstellar radiation field. Just for example, we have these pinwheels from the fair, and we put like so they start. If we put pressure of force on one side, they can start spinning. So the grains start spinning. At the end of the day, we have aligned grains with the magnetic fields. But what is RAT in a nutshell? So RAT was the most successful and tested theory. What is it in a nutshell? Grains should be regular or irregular grains. When they are exposed to an isotropic radiation field of wavelength lambda less than the diameter of the grain, they will spin up by differential torques from left and right-handed circular components of the light. But the material is assumed to be paramagnetic, and the Barnard relaxation or Barnard effect gives the grain a magnetic moment which causes it to larval pressures around the magnetic fields. Then because you cannot stop radiation. Radiation is continuously hitting the grain, so there is continued RAT on the grain facets, causing the angular momentum to align with the magnetic field. But if the radiation is strong enough and anisotropic enough, for example, in the expanding H2 regions, then the alignment axis can be changed from magnetic to radiation, from B to K. That's why I'm calling B rad to K rad. This theory, the rad was tested in the lab also and the paper was published by Abbas et al. In 2004, where they took a sample of dust grains, silicate dust grains, paramagnetic asymmetric silicate dust grains in the lab. The grains were levitated by an electrostatic balance. They were illuminated by laser from one side, and the grain rotation rates were obtained by analyzing the signal of scattered light. So as the intensity of the radiation or intensity of the laser on the grains was increased, the rotation rate was found increasing. So the light, the radiation was helping in spinning of the dust grains. So this was the only theory people tried to test in the lab. Now, I am not a theoretician. I was not putting any theory. I was just thinking to investigate these theories and whether I am able to test these theories with the data, with the polarimetric data, multi-band polarimetric data we have till date with the available facilities only. So in that part, some questions come. So first question is, how grain alignment or polarization efficiency behaves if we increase the radiation strength. Suppose I keep on increasing the radiation strength, what should happen to my dust grain? Can that continuous torque of the radiation destruct this grain? So for testing this question, we took our polarized observational polarization data. We collected a lot of data on the local bubble. So local bubble had a lot of published archival polarization, optical polarization data. These gray dots are local bubble. IC 5963 were our sample, which we observed from the Indian facility AIMPOL. And also LDN 204 was published by a group in the US. We collected all of it, and we plotted the polarization efficiency, what we got in these regions, with the radiation strength. We found some hints of increase in the polarization efficiency when we increase the radiation strength. Means as I increase the radiation strength, as I increase the radiation intensity, my spinning becomes faster and faster, and efficient spinning is going to give you efficient alignment, and at the end of the day, more polarization. So polarization efficiency was found to be a little bit increasing. But this is not the end of the test, because you can further increase it, right? But you should have observational sample for that. In the meantime, when we were doing these tests, a paper came in Nature Astronomy in 2019. That is from a theoreticians group in South Korea. So Thiem Hoang published a paper saying that RAT can become RAT-D actually. Your enhanced continuous radiation torque on the grains can destroy it. So there can be RAT-D, the destruction of the RAT. So we thought, okay, now this is another thing. We were already testing RAT, and now there's RAT-D. We thought, okay, let's collect all our data, whatever we have in different environments where the radiation is different strength, and let's see what happens. So we increased our sample. We included Orion Whale sample. So Orion Whale has a lot of optical and near-infrared polarimetric data available with our collaborators. We took that. We found the polarization efficiency again and plotted it with the radiation flux. We found a kind of saturation in the polarization efficiency. After a certain radiation flux, it starts getting saturated, which can lead to two things. One is either all my asymmetric or alignable dust grains are aligned, or my alignable dust grains are destructed. That's why I'm not getting any more polarization. So this work we are going to submit soon, but there is a hint of saturation in the polarization efficiency, but a disclaimer is there. The disclaimer is that this should be tested in multi-band polarization. We just did it for optical V and in some places IR polarization. This should be tested in multi-band. So there will be some shortcomings also on this, but we are working on that. So yes, Increasing radiation gives us hint in the increase in the polarization efficiency, but after a certain limit, it starts getting saturated. Second question on dust grain alignment theories, what happens to the grain alignment in the higher density regions? So I was showing Planck maps like lower density, they are covering whole sky maps. I was showing filaments also, I was showing some cores. But we want to see what happens to the dust grains when we go towards higher density from the lower density regimes in the star forming regions. There were simulations available actually already showing that when we go towards the higher density regions in the cores, there are polarization holes found. Polarization holes means a sudden drop in polarization. So this was simulation presented in 2018 by a group, and then there are some analytical calculations also presented by Thiem Huang in 2020, where they see that when you plot your polarization fraction with the density, here extinction is representing density here, your polarization fraction drops like a rock. So you have to find out why this is happening, why there is a drop in polarization, what are the causes of the polarization hole. But this was all theoretical. We went to observations. Some observations, for example, from a group of Chat Hull already published a paper in 2014 showing the polarization hole using submillimeter data. And using optical and infrared data, a group by Elvis and his team published a paper on pipe nebula where they see different slopes and where they see a drop in the polarization. It means something is happening to the aligned grains. But then we tried to test it with our observations. This paper also we are going to finish soon. So what we did is we compiled all the data like from optical, infrared, optical green, infrared in red, and the submillimeter longer wavelength data in the black. And we found that the polarization efficiency really drops, but there is a sudden drop after an AV of around extinction of around 18 magnitudes. So the polarization really drops faster after a certain density. So, but one more thing, these type of polarization holes are seen in the starless cores actually, not in the star forming cores, because star forming cores have enough radiation inside them which can further help in the spinning of the dust grains. So starless cores were mostly showing the polarization holes. We saw this in one starless core, L183. So we have observational evidence of drop in the polarization with the density. And explanations for that are that suppose your slope is 0, then your grains are perfectly aligned. Your slope is 1, you are not getting any grains aligned in there. And if your slope is between 0 to 1, then there can be some grains aligned and some not aligned, so there will be imperfect alignment. Okay, how much? 5 minutes. Okay, I'll finish in 2 minutes. So the reasons maybe there is a tangling of magnetic fields, because how grain alignment we are understanding grain alignment with the help of magnetic fields only. So magnetic fields may be getting tangled. There may be change in the grain properties, maybe they are becoming more symmetric, so they are not aligning with the magnetic field. And there can be decrease in the radiation, which is not helping in spinning the grains further. So grains are not spinning means they are not aligning. But some tests are pending. So next question is, can gas and dust collisions affect your grain alignment? Answer is yes. I will show some results, observational results. So if there is high density gas at the location where you are investigating magnetic fields through grain alignment, so if there are collisions, your grain alignment can be affected. And yes, we do see a drop in the polarization with the intensity of the gas, with the densities of the gas. And that drop, like blue and red, shows 2 different slopes of the drop, because that depends on the temperature. So higher temperature region may have more collisions. More collisions means steeper drop. Lower temperature regions may have less collisions means shallow drop, but there will be drop because of the gas and dust collisions. Last test, I'm just showing one slide here. How dust grain alignment behaves in different compositions of the dust. Because I was just talking about paramagnetic dust. What happens to it when it is diamagnetic or some other composition? So that test we are doing in a sample of AGV star envelopes, because AGV stars can be carbon rich, oxygen rich, and S type. So we selected some samples which have carbon rich diamagnetic dust in the envelope, oxygen rich silicate dust in the envelope. We found totally different results of polarization patterns. So our carbon rich shows radial profile of the polarization vectors. However, our oxygen rich shows a little bit, there is not much sample there, but it's not radial. So because silicate grains or silicate grains, they actually react to magnetic fields, but carbon grains do not react to the magnetic fields. They don't have free spins. So that's how we can say that the grain alignment also depends on the composition of the dust. And this is an overview of second portion of my talk, where polarization efficiencies seem to be saturating with the high intensities of radiation. Alignment of grain is affected when we go from lower to higher densities. Gas grain collision affect the polarization efficiency. We have seen that. And also paramagnetic and diamagnetic grains behave differently to the alignment to the polarization. And thank you. I just want to say here that magnetism is the only force apart from gravity that can shape the large scale structure of the cosmos. It tends to add up and survive. Thank you.
Thanks, Archana. Questions? Ishwar?
Yeah, thanks, Archana. Yeah, hello. You showed, no, on x-axis luminosity per parsec square versus alignment efficiency. That's very
yes, I showed two actually.
Yeah, yeah. So, so this x-axis is the distance from the Wobbe
Yeah, so your radiation source, you should know the distance to your radiation source and luminosity properties of that source. Then only you will be able to know the flux of that radiation.
Okay.
Yeah.
Have you seen the same dependency on the temperature?
Oh, temperature, we are analyzing that.
Oh, because rad D will comes into picture if you have
Definitely, yes, because high radiation means more temperature. So we should see similar results in temperature, but that part is not done yet.
Oh, okay. Yeah, good.
Yeah.
Yeah, Archana, you explained nicely the effect of composition on the grain composition, but can you tell something about how the grain size affects your conclusions, especially on the polarization part?
Yeah, that's a nice question. So actually, sorry, if you go here, whatever grain sizes I was talking about was submicron size. But when you go to the colder regions, which are probed by your millimeter wavelength, your grains get bigger, submicron to micron sizes, and also get a little bit more spherical or circular. That's where grain alignment is affected. Yes, that really affects the grain alignment, and if they get bigger, first you have to go to longer wavelength, and even if you're not getting polarization, means your grains are getting more symmetric.
Ma'am, so if in the previous work that you were showing where magnetic field alignment with the structures was shown, and you had shown some graph from your student.
Oh, okay, yeah. That thing is there in his poster, but yes.
Yes, ma'am. Yeah. So over here, when you are using, this is like near optical band, and that is using more higher wavelength. So
that is Planck.
Yeah.
Yes.
Okay.
Yeah.
So that gives you like bigger samples of B, right? The larger scale structure.
Yes.
I was also wondering, is there more correlation about the density regions, these kind of band sample? Because there is also a correlation between the density of the filaments and the magnetic field orientation, right?
Yes. So that thing we haven't done here because we did not have very high sensitive or high resolution submillimeter data. But you could see here in this one. So this is some millimeter. You can see that towards the higher densities, the magnetic fields are mostly perpendicular. It has been found on all the results of Planck. But towards the lower densities, magnetic fields start following that structure instead of being perpendicular.
So there is no particular this thing.
The correlation between position angle and the densities, that's what you're asking?
The wavelength that we are sampling. Like, so for example, if you use near like tracers, like carbon tracers at different lines basically correlate with different
molecules.
density structures,
yeah.
right? So,
yeah.
is there any correlation between such optical band and radio band's density over here?
In context of polarization?
Yes.
Or magnetic fields? Yes, most of the cases, for example, it seems like magnetic fields are found connected, but there are some gaps. Actually, we have to fill those gaps using far infrared observations. So what is happening here is you have optical, you have infrared, then you suddenly jump to some millimeter. You don't have that far infrared thing, but if you have it, in some of our results from SOFIA we have it, we do see a connection, but there is a slow change in the orientation.
One last question.
Hi ma'am, very nice talk. I'm asking about, is there any observational evidence about the mechanical alignment of lustrines?
Nice. It's a hard question, but yes, people are now understanding the magnetic field strength also along with the outflows in some regions where you have outflow signatures. So they put some kind of mechanical forces on their surrounding, and then they can disrupt the grain alignment, which will change your field geometry as well as field strength. So, but no observational evidences are like published yet, but there are efforts going on in that direction.
Okay, for my source, I'm observing like along the direction of my protostella jet. I'm seeing that the dust are
maybe we
more
can continue
efficiently.
this discussion over
We
tea
can
later.
talk over
Yeah.
tea.
Okay.
Yeah.
Thank you, Archana. We now move on to the last talk of the session by Saranya Shur. He would be talking about fluctuation dynamos in galaxies and galaxy clusters.
How do I add this? That's the point. Yeah. Oh, so this one doesn't work, the laser? I see. Okay, so I have to be ambidextrous. Anyway, so first of all, thanks to the scientific organizing committee led by Jasjeet to give me this opportunity to present my work, and also thanks also to the local organizing committee, so some of whom I have known for many years now for organizing this event, and I know that it's a tough job to organize this kind of conferences. So today, what I'm going to talk about is fluctuation dynamos in galaxies and galaxy clusters, and basically, of course, I mean, like in half an hour, it's impossible to talk about this topic. It is such a vast and developed field. So what I am going to give you is a flavor of the kind of work that is being done in this field, okay? And so that that's the take-home sort of message that you can carry with. So just to give you an example, so this is one of those fluctuation dynamo generated fields in a numerical simulation. And here the field is strong in the yellows and the blue regions, and also the field in the plane of this slice is shown by these arrows. The length of the arrows denote is proportional to the strength of the magnetic field. And what is immediately striking is that there are all these different folded regions, okay? So you can see the arrows moving here, and then it is folded backwards, then here, and then there. And this kind of direction reversing folded fields is a fundamental property of random shears, which I'm going to come in a minute. So here is the outline of my talk. So I will start with a brief introduction to fluctuation dynamos and present to you in a very distilled form, the properties and a concise history of the developments in this field so far. And the main part of my talk is going to focus on two aspects. So one is theoretical, where I am going to try to address this question of how does the dynamo saturate, okay? And I will come to that in a minute. And the other part of the talk will focus largely on what I believe is one of the most important things, and that is to look for observational signatures of fluctuation dynamos. And in this context, I'm going to share with you some results in the context of young galaxies at high redshifts, and also probing the properties of polarized synchrotron emission in galaxy clusters. And lastly, I will talk about some of the work that we have been doing on large-scale velocity shear and its effect on the properties of the magnetic field. And as is customary in any talks, I will share with you some conclusions. So to begin with, fluctuation dynamos, they are at the heart of magnetic field generation in galaxy clusters and also probably in the interstellar medium. And I have just shown here some 3 important references. The list is actually endless. And one of the last references here is by Frederick Gent et al. In 2000. Actually, the paper got published this year in January. So this is one of the first papers of non-ideal MHD simulations in the context of interstellar medium magnetic fields. So as with any dynamo, as the name suggests, I mean, we are all familiar with dynamos in some sense, because if you have rode a bicycle in your young days, you would know that there is a bicycle dynamo where when you pedal, the mechanical energy gets converted to electrical energy, and you have a light in front of you that shines through. So similarly, in fluctuation dynamos, you basically tap the kinetic energy in fluid motions to amplify the magnetic energy, and the growth of the magnetic field actually happens by an infinite sequence of random stretching of the field by turbulent eddies. And I'm going to comment on it going further. Sorry, I miss a touch screen here. So this is a simplistic example that if you have some shearing flows which are stretching the magnetic fields, and it was shown by a paper by Zeldovich, Molchanov, Rusmaykin, and Sokolov in 1984, that if you can repeat this for an infinite number of times with this area preserving random shears, then on the average you get a net growth in the magnetic field. So that paper is quite old, but I still remember that paper because when I sat down to work on it, the mathematics was simply very elegant. I mean, it was just beautiful mathematics, and the brilliance of those authors just shone through that paper. So this was like, again, like done by various other people. So this is an old book by Childress and Gilbert. And what the important point to note here is that the magnetic energy evolution is actually governed by a combination of different terms. So first of this is a stretching term, which is proportional to the rate of strain tensor, which is denoted here by this capital S. Then this one is the advection term, because it just goes as u dot grad. And then this one is the term which arises just from compression, because it's proportional to divergence of u. And this one is the standard dissipation term, and its effect is just to reduce the magnetic energy. And this one is mainly negligible in subsonic flows. So I will come back to it in a few minutes. So before that, so what I want to show you here on the left-hand side is the magnetic energy growth from a paper by Amit Seta and Christoph Federer in 2021 for a solenoidally driven turbulence simulation at 512 cube, where turbulence was forced at half the scale of the box. So you need some turbulence to build up the field, okay? So ideally in simulations, you do it by an externally driven artificial body force, or like in nature, it would just happen by gravity or even by simple hydrodynamic instabilities like the Rayleigh-Bernard convection. So the simple convection that you encounter every day while boiling a pot of water. So what this shows here is that there is a phase of exponential growth, and then sort of it saturates, it goes and reaches a steady state. And I would have been happy to tell you more about all the different things that we observe here, but I don't have time for that. On the other hand, so here I show these two-dimensional snapshots at these two different phases. So so this one is from the kinematic phase somewhere over here, well, not from this simulation. And this one is again the saturated phase where you see this direction reversing folded field structures. Now, to get back as to what I was discussing, so the field grows exponentially until a saturation process kicks in. And here is a summary of the main properties. So the beauty of the fluctuation dynamo is on this fact that it is generic in any random or turbulent flow. You don't need density stratification. You don't need any other stringent conditions. The only thing is that you need a magnetic Reynolds number which is larger than some critical value, so which is about 200 in subsonic flows. And this happens because the magnetic, if you look at the magnetic energy evolution, the magnetic field growth equation, so that's basically the induction equation. So the growth of the magnetic field is a delicate balance between the inductive term and the resistive dissipation term. And therefore, you need a critical magnetic Reynolds number. The other thing about this dynamo is that the field is amplified on something known as the eddy turnover time scale. So turbulence produces a lot of eddies. So I think Ishwarya showed a picture of Leonardo da Vinci's turbulence picture. So it's a collection of actually eddies, and you can imagine that if the eddies are of a length L and V subscript L are the velocities on that scale, then you can construct a time unit out of it, and you can show that for subsonic turbulence it goes as L to the power 2/3, for supersonic turbulence it goes as L to the power half. Now, what that tells immediately is that the smaller the eddy, the faster is the eddy turnover time. So they are the ones who will grow the field fastest. Okay, and the growth time in case of galaxy clusters, it's about 0.3 gigayears, and for galaxies it's only about 10 to the power 7 years. So these are much less than the lifetime of these systems. The downside is that the fields that you get from this dynamo, they are correlated only up to the scale of turbulence. So if you so one of the famous pictures of magnetic fields in galaxies comes from the grand design spiral M51, where you can see this large scale magnetic field on the scale of the galaxy itself. So that is produced by a different large scale, different dynamo process called a large scale dynamo, not by these ones. So these are mostly, you will find fields which are on the scale of the turbulence, and the field structure appears to be highly intermittent in the sense that they will have, if you look at the probability distribution function of the field, then they will have these heavy tails in this distribution. Okay, and then this one also, so this is a log normal, you can fit it by a log normal distribution here, and the intermittency actually appears to be stronger in the kinematic phase when the magnetic field is growing exponentially, and it is weaker as compared to the turbulent kinetic energy. And then sort of as the magnetic field saturates, the intermittency level also decreases. So now let me sort of move forward and give you a concise history of this field. So the fact that a weak seed, you can amplify a weak seed magnetic field in a three-dimensional flow was first studied by Batchelor in 1950 in this Prokhorovsky paper. But the accepted theoretical framework that was only developed by 1968 by Kazantsev, and he developed this thing for something known as a delta correlated velocity field. So which means that if you take the 2-point correlation function of the velocity, so velocities are functions of position and time, so the time dependence is a delta function. Okay, and so therefore, and this is not a limitation of the theory, it is just that Kazantsev was smart enough to understand that the only way in which you can solve the resulting equations was by making this kind of an approximation. So in those days, there were no supercomputers to do it for you. So, so this gave rise to the linear theory, so which was limited to the early kinematic phase of growth. And then there were other big players in the game, like Zeldovich and Kulsrud and Anderson and all, who enriched this subject even more. But after 1968 and after 1980s, there was a sort of lag in development of this field, and I personally believe that this is because of the discovery of large-scale dynamos, which dominated the development in this field. And the pace picked up again only in the early 2000s when simulations which were mainly motivated by this work of Meneguzzi, Frisch, and Puke in 1981, so they began to reproduce what is now known as a Kazantsev spectrum, which means that the magnetic energy spectrum as a function of the wave number goes as k to the power 3/2 times some function. So this is called a McDonald's function of zero order. It's just a fancy name. It's nothing but a modified Bessel's function of the second kind. That's all. So since then, this dynamo has been explored in both subsonic and supersonic turbulence, and also in self-gravitating environments. I think in one of the earlier talks, Jasjit raised this point about POP3 star formation, magnetic fields in star formation. So in fact, I did the first simulation in 2010 of this kind of a dynamo working in a collapsing environment with pure self-gravity put in. And also there are other works by Franco Vazza in the context of galaxy clusters and all. On the theoretical front, there are also developments, that is to extend this theory from delta correlated to finite time correlations, and also to introduce nonlinearities such as ambipolar diffusion and all. And recently the pace also picked up in terms of developing a theory for all this magnetic field amplification in the context of primordial star formation by Chris Mackey and Zhu and Lazarian et al. So now let me come to the first aspect, so what is known as the fluctuation dynamo saturation. So the saturation actually happens on a scale by scale basis. So what I mean by that is that if you have a sufficiently high fluid Reynolds number flows where the velocity field consists of multiple scales, the magnetic energy or the magnetic field will be first amplified on scales small enough where the magnetic Reynolds numbers exceed the critical magnetic Reynolds number at that scale. And there the magnetic field will grow and then it will sort of saturate when the energy at that scale, the magnetic energy at that scale becomes comparable to the energy density in the fluid motions. And then what happens is that the neighboring scale, which is at a lower L, so which is at a higher L, sorry, so that can still continue to amplify the field because it has larger energy, and so on and so forth. So it's like an inverse cascade process which extends almost up to the forcing scale of turbulence. And this has been sort of said that suppression of field line stretching due to the growing magnetic tension is one of the reasons why this magnetic field saturates. However, so there are certain open questions which I am sort of addressing right now, and that is it possible to limit the growth if strict incompressibility is not imposed? And this mainly arose from the fact that the simulations by Shekoshin and all, they are incompressible by definition. So they put in divergence of U to be 0 in the simulation. Okay, so I personally feel that they cannot address this question because of the nature of the code that they are using. And can magnetic pressure oppose compressive motions? And most importantly, that is a direct question, that is suppression of field line stretching the only player in dynamo saturation, or is there some other players as well? So to examine this thing, so we carried out all these non-ideal compressible flow simulations with a flash code, and I will focus just on 3 MHD simulations with non-ideal turbulent flows at magnetic Prandtl number of 1, so which is just the ratio of the magnetic Reynolds number to the fluid Reynolds number, covering a regime where the compressibility effects are weak. So this is a subsonic turbulence, this is transonic, and this is supersonic, and these are mostly the fluid Reynolds numbers. So here, what I'm going to show you first is the nature of the alignment between the density, the magnetic field, and the components of the Lorentz force. And what I show here in this column is you take the unit vector of the magnetic field and you take the unit vector of the gradient of the density, and then you see how they are aligned. And what you see is that irrespective of the compressibility of the flow, the unit vectors, they are all aligned perpendicular to each other. And the degree of this orthogonal alignment appears to be stronger in the saturated phase. Whereas if you look at the unit vector of the gradient of the density with the unit vector of the gradient of magnetic pressure, so which is the first term in the Lorentz force, so what you see here is very interesting. So in the subsonic case, there is an anti-parallel alignment, okay, and this actually becomes stronger as the magnetic field saturates. And this is just a manifestation of the fact that as the magnetic field saturates, the magnetic pressure is trying to oppose further compression of the field lines. And this happens because when you stretch something out, there is also compressive motions, okay, which are perpendicular to the stretching motions, which are trying to reduce the cross-sectional area of the flux tube. But since the magnetic pressure is large enough now, because you have the stronger magnetic field, it will resist this compressing of these field lines. It will try to decompress this thing. Now, on the other hand, when you look at the transonic and the supersonic cases, what you see is that in addition to this anti-parallel alignment, there is also the emergence of a parallel alignment. And this happens because, and this mostly happens in the kinematic phase of the dynamo, okay? And this mainly happens because as you increase the effects of compressibility, there are two things that are happening. So the magnetic field is getting amplified by density compression because now you can have shocks which will also lead to some magnetic field amplification. And on top of that, you also have these magnetic fields which are being amplified by the dynamo. And by dynamo, what I mean is that these magnetic fields are being amplified by vortical motions, okay? And not necessarily the place where you find strong vorticity will correspond to regions of strong density. Okay? So because of that, you will find this parallel alignment also in addition to this anti-parallel alignment. Now let me come to the next question, that is field line stretching the only player in the game. So because that has been something which has been proposed, and it has stayed long for more than 20 years now. So to investigate this, so what I did was, you can write down the evolution of the mean magnetic energy in some form. Okay, so this is not very difficult to derive. So you just take the induction equation and dot it with a B, and then you try to express it in terms of the rate of strain tensor, and the remaining terms just follow. So now to see the effect of whether there are any other agent for the dynamo saturation. So what I next did was I calculated the probability distribution functions of each of these terms, and you look at the mean and the standard deviation of these terms. So here is what I have plotted here. So these are the evolution of the mean over time for all these different terms, which are color coded. So this blue one is for the stretching, the green one with the stars is for the compression, and the red one is for the advection, and the purple one is for the diffusion, and this is the black one is just the sum of the means. Now what you see is that for so this is for subsonic, that's for supersonic. So what you see is that for subsonic, it does sort of conform to the fact that field line stretching is the major agent in dynamo saturation, because as you go towards the saturated phase in this particular simulation, the saturation starts from around some 1380 turnover times and all. So there is a growth, and this growth happens because of this field line stretching and also by enhanced diffusion. And most importantly, you see that the compression term remains very close to zero. It does not play any role. On the other hand, in the supersonic phase, you immediately see that it's actually the compression of the field lines which is having the major effect, and the effect of the local field line stretching is actually subdominant to this compression all throughout the evolution until you reach some part of the saturated phase where it tries to dominate. So in a sense, this indicates that the statement that field line stretching is the only player in saturating the field and suppression of the field line stretching actually holds true only for incompressible flows. It's not true for compressible flows like this one. So that is something which is new. Next, I will now focus on how we can obtain certain quantitative estimates of observational signatures of fluctuation dynamos, because at the end of the day, any theory has to stand the test of how it can sort of reproduce certain observational results. So in this context, I'm going to talk about two things. I mean, both of these can be talks in separate, in a separate, but I'm just going to throw some basic results at you. So first of these is fluctuation dynamos in young galaxies, where Faraday rotation measure observations through high redshift galaxies when the universe was only about 6 giga-years old revealed that they host micro-Gauss strength magnetic fields. Now at that early age, it's impossible for the large-scale dynamo to operate and order the field on the scale of the galaxy itself. So such fields can only arise from fluctuation dynamo mechanism. Now, having said that, it is important then to probe what is the degree of coherence of these fluctuation dynamo generated fields, and how do the estimated rotation measures compare with the observations. And so I'm just going to show two slides on this. Where is the mouse? Sorry? No. Yes. So let's concentrate on this curve here. So where I have plotted the standard deviation of the normalized RM as a function of the eddy turnover time, and the standard deviation is necessary because the fluctuation dynamo generates fields which are statistically isotropic. Okay, so if you calculate the mean RM, so that is going to be 0. So what you see over here is that so these different lines correspond to different simulations with different regimes of compressibility. So 0.1 is like a very subsonic case, and 2.4 is a supersonic case, and then this one is a transonic case. Now, what you see here is that irrespective of the flow compressibility, so in this kind of different variety of flows, the fluctuation dynamo generated fields still show very similar statistical properties in the sense that the sigma Rm is very close to about 0.45 to 0.55. So what this tells you is that these fields are actually arranged on a scale at least half the correlation scale of the turbulence. So in the galactic context, if you put in some numbers here, for let's say for the electron density some 0.1 to 0.3 particles per centimeter cubed, and some RMS magnetic field of 3 microgauss, and then some length scale of turbulent motions of 100 parsec, then this leads to a random RM of around 16 to 48 radian per meter square. Yes. So which sort of agrees with the observations of Jamie Farnes et al. And all. So one of the important questions which I don't have the time to sort of go into is, does this coherence arise from volume filling fields or from the rarer intense fields? So this I have addressed in this plot, so maybe I can share with you later. So now the other thing is that the Faraday RM only provides information about the line of sight component of the magnetic field. On the other hand, there are two other observables, so which are this synchrotron emission and its polarization. So that provides information on the magnetic field in the plane of the sky. So in the context of magnetic fields in the intercluster medium, so we studied the statistical nature of the total and polarized synchrotron emission, the effects of Faraday depolarization, beam smoothing, and so on and so forth, and also on the effect of turbulent driving scales on the observations, on the observables by performing high resolution broad bandwidth synthetic observations in these frequency ranges. So I will not have much time to show this stuff here, but one thing which I want to tell you is that most of the observations of galaxy cluster magnetic fields are usually at this wavelengths of around 1 to 1.4 gigahertz and all. Now I would like to point out here to you that at these frequencies, so what you see here is that in this row, it's the polarization intensity, and this one shows the fractional polarization, so which is just the ratio of the polarized intensity to the intensity. So what you see here is that there are these low frequencies of 0.5 and 1 gigahertz. There's a lot of Faraday depolarization happening, because of which you see all these small scale structures over here. And while that is absent in the case of high frequencies at 6 gigahertz. And I think this will sort of will not give you, if you are observing at these wavelengths, it is not going to give you the correct magnetic properties of the ICM properly. So in the remaining minutes, so I just skip this because there is not much time. So polarization fraction at different scales. So one of the things which I'm doing currently with my postdoc Naveen, so who is here in the audience, is to study the effect of large-scale velocity shear on the properties of the Faraday RM and the polarized synchrotron emission. Now, large-scale velocity shear is something which is very common in many astrophysical flows, starting from solar, in the case, solar and stellar convective zones, to galaxy clusters where velocity shear happens on larger scales because of the sloshing of the gas during mergers. And this can potentially impact the growth rate and the properties of the magnetic field. So what Naveen is doing is that he is studying these numerical simulations of non-helically forced fluctuation dynamo with a large-scale linear shear flow. So these are nothing but weak initial fields subjected to some nonlinear turbulent driving with a background velocity shear. So this is an example of what differences do you get. So here is all the magnetic field properties and everything from a fluctuation dynamo simulation without shear. So these are all well known. So the most important thing is that when you compute the sigma rm in the 3 directions, then all 3 directions are equivalent now. So therefore you get similar values, okay, in all 3 directions. Now when you put in a large scale velocity shear, a background shear, so this is what you tend to see, and this is for something which is the strength of the shear times the eddy turnover time is of order 1. So this kind of a situation arises in galaxy clusters. And what you see here is that the By component is almost 4 times the Bx component, so 3.624. And when you compute the sigma rm, you see that along the y direction it has a large, almost a large scale feature, because of which so it dominates all the other 2 components. So it does matter now in the presence of shear in which direction one is looking at. So I think I would just conclude here and say that just a few words, that fluctuation dynamos are an important mechanism for magnetic field amplification, and there is a better need to understand the saturation mechanism for large magnetic Prandtl number system. It is equally imperative to look at observational signatures for a meaningful comparison between theory and observations. Okay, that is the most important thing. And here I believe that in addition to Faraday RM, synchrotron emissivity and polarization signals are indispensable for weaving a coherent picture. So I just want to thank you, and thanks to my DST grant, which is now over. And most of these simulations, whatever I've shown you, so these are done with Indian facilities, okay? You don't need to go abroad to do this kind of runs, okay? You can do it here. If you need more information or more understanding, please drop me an email at these two numbers, these two email IDs. And I just want to take a minute to tell that I do believe that science is certainly not a monologue, so it's a multi-log for me, if there exists a word like that. And I just want to thank many people, especially those who have written papers on this thing, with whom I have had direct interaction or with whom I have never met, and I will possibly never meet because their lifelines will not match with mine. So they have inspired me to be in this field and to think about physics almost every single day. So thank you.
Yeah, thanks, Aranya. Questions? Mamta?
One is, what is the direction of this shear that you have shown in the last plot? And the other one is that in case of the small scale fields rising because of dynamo, what is happening to the diffusion? Are they being diffused or are they saturated?
Yeah. So one of the things, so the answer to your first question is here. So the shear is, so it's in the y, which is varying along x. So this is the large scale velocity that we put. Yes, yes. So that is the reason. The second thing is that if you consider the fluctuation dynamo where you are stretching the field, of course this comes at a cost, because if you stretch the field in one direction, you are compressing the field in the other two directions, right? In the perpendicular direction. So then what happens is you will end up squeezing the field to small enough volumes, and this growth will stop when the diffusion across this particular length scale will be equal to the stretching. So that's when the saturation will happen.
Does that then go towards the large scale dynamo? Or
No, it will not go towards the large scale dynamo. So it will go only up to the forcing scale. So
yeah, So my question is, what is the role of gravity in large scale dynamo? Basically, if you have a dwarf galaxy or a large scale galaxy, so how does it play a role in, what are the time scale for this dynamo process?
In case of what? Elliptic?
In case of gravity.
So gravity, see, the thing is, ultimately gravity will drive this turbulence. Okay, like in whatever real system that you see, it will be gravity. So even in galaxies and clusters and all. So the time scale for that